Welcome back, geologists, for the second half of the plate tectonics of the Cenozoic. And a very fun time to learn about the plate tectonics because it's the most real to us because we'll relate to it. We're going to be looking at the Quaternary Period, which is just a very, very sliver of geologic time in comparison to the Paleogene and Neogene. You just learned about the various parts of the continent and how they were impacted by plate tectonics during three-fourths or more, really, of the Cenozoic. And now we're going to take a look at what happens towards the end of the Cenozoic. So you're looking at a really great national park. It is Grand Teton National Park, which is just south of Yellowstone National Park. Definitely a worthy place to visit for numerous reasons besides its beauty. But its geologic history is phenomenal. And we'll kind of look at this particular park here shortly. So we're looking at this segment of time. The Quaternary is made up of the Pleistocene. Most people refer to it as the last ice age, but remember its name means most new. Holocene or Holocene represents entirely recent. So let's take a look at this. 2.6 million years is what starts the last ice age and goes to about 10,000 years. You'll see some information that it warmed somewhere between 11,000 and 12,000 years ago, which is true, and maybe even sooner than that. But the last flux of ice that came through during the tail end of the ice age melted in different speeds depending on which ice sheet you were looking at. And we'll get to that shortly. So we're at the top of the time scale. You realize that means we only have the life forms to do of the Cenozoic and then, of course, hominids. So some of the real fun stuff's fixing to come that you'll enjoy because that involves the Ice Age animals and then the evolutions of humans. So let's get started and get the plate tectonics out of the way. We do refer to the Pleistocene and its general term as the last ice age, but you need to realize that this demonstration that you see right here from NOAA, a map showing you the extent of glaciation during the Wisconsin ice cycle, is not the full story of the Pleistocene. I'm not saying they're wrong at all. This is a look at the greatest glacial extent, so it's spot on. What I'm telling you is that there were multiple cycles of glacial advances and retreats. In real recent time, and I mean within the last few years, new data has surfaced from studies done in North America that took our old theories based on a number of pieces of evidence that we'll look at shortly of the 4 standard ice fluxes from the Laurentide, and now we know that there are a total of 13. If you go over to other parts of the Northern Hemisphere like Europe and Siberia, they had 20 of these cycles where it was warm and cold, warm and cold. But in addition to glaciation, we can't forget that the Pleistocene was a very important time in volcanism. And it set the stage for a number of important volcanic events that we'll look at. Let's get back to the Cascadia Range. It seems like we keep coming back there, right? This is Mount St. Helens, and this would be an example of Pleistocene volcanism. When you think about Mount St. Helens, this is a very young volcano. Not old at all, several 100,000 years old, no more than 500,000 years old. And when I went to see it on my sabbatical, I was so humbled by what had happened, knowing the story of the 1980 May 18th eruption. And you have to realize that this volcano became a concern for USGS, United States Geological Survey, back in 2004 and 5 when new activity started to be monitored in terms of magmatic rising and geothermal energy and all the clues that indicate that volcanoes are starting to be activated again. Mount St. Helens is not done. She has a repetitious history during her short existence of multiple eruptions similar to what she did in 1980. So we're not done with the Cascadia Range. Juan de Fuca is still there. It's still subducting. And as long as it's subducting, we have active volcanoes like this in Mount Rainier. We have active volcanoes like potentially Mount Shasta. And you look at Mount Olympus, it's probably not as much of a chance of reactivating, but it could. Mount Hood, all of these famous volcanoes, Lassen Volcanic Field. So each of these areas represents the Cascade Range, and the Cascade Range was active during the Pleistocene and still is today. This is Lassen Volcanic Field in Northern California, and when I went there on sabbatical, I was taken by actually seeing it, besides reading, was understanding that Lassen has every type of volcano, from a shield volcano to a composite volcano to a lava dome to a plug dome, which is like a lava dome but bigger, and even little cinder cones. So they had everything. It was really fascinating. It has a neat place that's called Subway, which is a lava tube that you can hike through. It's a fairly short one. But it's a neat park, and it's geothermally active today, and it's the result of the Juan de Fuca plate subducting under North America in Northern California. So active, and it started in the Pleistocene epoch. All right, big news in terms of parks is Yellowstone. Yellowstone is a gorgeous place. And you look at this, and it takes people's breath away when they see Artist Point in Yellowstone, and it should. This is right at the observation point. And what I'm wanting you to get, besides this gorgeous waterfall at the end, let's look at the rocks that lead up to it. The stuff on the sides, right in here and in here. That's rhyolitic ash. Now, you don't get ash like that by accident. These happened because of these gigantic megacolossal and supercolossal eruptions that happened over the last 2 million years, not once, not twice, but 3 different times. And this enormous caldera, it's really 3 calderas to be exact, but it makes kind of one big large one. These calderas represent these gigantic supervolcano eruptions, and the caldera measures 76 by 45 kilometers wide. So really, as you come into Yellowstone, there's a big rim, and you could drive down into it. And inside of it is all the materials that were laid down during these incredible volcanic eruptions. Well, that stuff started and did its work during the Pleistocene. All of the Yellowstone story really is limited to Pleistocene and then a little bit in the Holocene. So part of the area has risen because of resurgent dome, and it reactivated some volcanism in the form of producing volcanic tuff, which is still rhyolitic material, isn't it? And it laid down some lava flows in the park and things like Obsidian Cliff that we mentioned earlier. So this is a very important story of the Pleistocene, and also important to timing of ice cycles. I mentioned the Grand Teton at the beginning, but let's focus on the Grand Teton Fault, because that's what's responsible for this just rather impressive landscape that you see there. Part 2 to the story is glaciation during the last ice age did the carving of the mountains. But nevertheless, 10 million years ago, during the Miocene epoch, we had the Grand Teton Fault get reactivated. As the land began to stretch and tension happened, we formed these massive faults. And here's essentially what happened. The valley floors dropped, and when I mean they dropped substantially, in some cases up to 20,000 feet, which is what happened to Jackson Hole, Wyoming. That's a famous tourist destination. And if you go to the Grand Teton National Park, you'll likely stay in Jackson Hole for a night, if that's not where you kind of make your landing spot, in other words, where your staging location is. And it's well worth a visit. It's a beautiful town. When you think about the Grand Teton Park itself, the park is fairly big park, but what's famous about it is this landscape right in here. And there's a couple of really beautiful places to visit within Grand Teton. My favorite is Jenny Lake, and you need to plan your trip to get there early in the day to see Jenny Lake, like first thing around 5 or 6 in the morning before it gets too crowded. But it is the spectacular view, and you can take a boat ride to get to a fairly recluse part of the park that you can see and get up there and take some pretty remarkable hikes. Nevertheless, during this activation of the faults, we would have some pretty enormous earthquakes that would have been at least major on the Richter scale or higher. And these earthquakes would have cracked and faulted the rocks even further. And when this did, the crust broke, the stress released. And it pushed up the summits 7,000 feet above the floor and dropped the valley floor lower than it used to be. So there's this just huge spread between the top and the bottom of the Grand Teton versus the plains. And that's what's so distinctive about this park, besides the horns that you can see, U-shaped valleys and so forth that are carved by valley glaciers. Believe it or not, Arizona has a Pleistocene story to tell and even a Holocene story to tell. But its volcanism really became prevalent during the Pleistocene. On field course each year, we go to Arizona and we go through Flagstaff, which is exactly what you're looking at right there. This is San Francisco Peaks, and San Francisco Peak used to be a conglomerate type set of volcanoes, and then, I'm not kidding you, there's 600 little cinder cone volcanoes, dikes, and so forth that go through the area that are related to igneous activity that occurred in the last 6 million years. So you're looking at Miocene and Pliocene epoch time. And then certainly Pleistocene. And in the Pleistocene, most of that work happened. So the most recent of those eruptions came from Sunset Crater, which is a small cinder cone volcano that's just west of this, going just maybe 10 miles north of Flagstaff. And it's a national monument, and it ought to be. It's a beautiful set of basaltic flood basalts that you can take some really nice hikes through to see how these systems are formed. That thing actually erupted in 1064 AD, and there was a civilization that lived there. So there's two parts to the park. There's the volcano side of the park, and then there's the archaeological side of the park. They're two different sections of it, but it's well worth your time to stop and get a look at this remarkable Pleistocene volcanism. The Raton-Clayton Volcanic Field is a famous place where Capulin Mountain is located, and it's a national volcanic monument, by the way. And this is a cinder cone, but it's a field of cinder cones. These cinder cones represent volcanism that occurred at the tail end of the Pleistocene 62,000 years ago, and is part of a large surge, the very final surge of volcanism that's been occurring since about 8 million years ago. And it's actually, this whole section is related to the Rio Grande Rift. It may not erupt again, but new cinder cone could evolve at any time and start to surface and create volcanism. Cinder cones are known for being kind of short-lived. In other words, they produce fluxes of volcanism and then they kind of turn off. But some cinder cones can actually blend with the continental crust. They're usually hooked into some kind of a blending situation where it produces mafic eruptions, but with a little bit more personality than just a full-fledged flood basalt. However, there are a number of flood basalts out in this region. So as you travel through New Mexico, it's a complex system of different types of volcanoes that have erupted and different personalities of the same types of volcanoes that have erupted. But Capulin is famous for this area. This is the Valley of Fire, and it's a place that's in New Mexico representing the same Rio Grande Rift stuff, and it erupted in the Holocene 5,000 years ago. So it's a very, very young lava flow, and I highly advise going to this, it's BLM lands, and it's a kind of a recreation area, and it's a neat place to really walk through and see some thick lava flows, which were flood basalts called the Valley of Fires. Now, the Grand Canyon, we talked about a series of things from the Grand Canyon all the way from the Precambrian to now. And I think it's important that we connect and link starting in the Precambrian. Just about every time that we've talked, we've had something to talk about with the Grand Canyon, right? We kind of skipped over the Mesozoic for Grand Canyon simply because there are no rock layers that are in the two major sides of it, the North and South Rim. Away from it, as you're coming into the plateau, there certainly is, but the Grand Canyon has Precambrian aged rock at the very bottom of it, the basement rock, and then the walls of it is primarily made up of Paleozoic rocks, and a bulk of it at the top being Permian. Well, what's really fascinating is that we've had a couple of really important things happen to the Grand Canyon in Pleistocene and certainly Holocene time frame. So there is a theory that some ice dams formed during the Pleistocene that created breakage of those ice dams, creating mass flooding, which led to some of the variations of dip or grade in the Colorado River. This is before the Colorado was ever tamed, which is important to note because as we put dams on the Colorado, that changed the ability of it to erode the same way it did before those dams were put in. Important to also note that during the Pleistocene, we started getting carving of this canyon that began. It even started back in the Miocene, somewhere around 6 million years ago, as the Colorado Plateau continued to be uplifted, starting from that 20 million marker all the way up to about 6 million years ago. And as it tilted, rivers began to flow and started carving through this remarkable set of layers of rock that we call the Grand Canyon National Park today. So we know it's still carving, and a lot of that activity is important even until just 50 to 100 years ago, when we put a couple of important dams on within the last 50, 60, 70 years. That's changed everything in terms of how the Grand Canyon operates. I should also make note that there's been recent volcanism in the last few million years, especially on the west side of the park. So there's some lava flows that essentially did the same thing I mentioned as the glacial dams did to the geology down in terms of creating different grades of the riverbed. So you don't see that same kind of volcanism at the North and South Rim. You have to go further west to see it, but it exists in the Grand Canyon. Well, that brings us to the story of the Pleistocene, and most of you are anxious to hear this. If you took physical, which you should have, this is going to, some of it be repeat, so don't tune me out because there's new information that you've never heard, but it should be like, oh, I know what that is. Bottom line is, we know glaciers were here. We don't have the ice, except in a handful of areas left, to tell us that glaciers were here, but what we have is a ton of proof. And there's a really famous guy by the last name of Agassiz who has a lake, or did have a lake named for him in Canada. And he was the guy that really pushed for the concept of glacial erratics. And people didn't believe him. Well, his theory has since been proven. We know it's true. And this is big stuff because as we begin to piece together the story of the last ice age, this not only involves the geology, this starts getting into archaeology, which is our human ancestry. And humans have always been interested in where we came from, how we changed, and any evidence of our past existence. And certainly the last ice age, humans were around by that time. When we talk about the last ice age, there's a couple of things I need to visit with you about. First of all, we've already mentioned that they came in cycles. We'll revisit that again in a minute. But there's two very different, really three very different types of glaciers that we're going to look at. The first is continental. And when you think of continental, I'd like you to recognize that the northern hemisphere in particular, with some of the southern hemisphere being Antarctica and certainly Patagonia, which is going to be this area right in here along South America. But look up here and notice the northern hemisphere has distinctive glaciation. It's kind of backwards from what we saw during Pangea time frame when Gondwana land was all frozen up, right? So it's just the opposite. We get up the northern hemisphere that's doing the work this time. Up to 30% of the Earth's surface is covered by these glaciers. That's a lot. Today, we don't have that much, not even close. And so these were not runts. These continental glaciers that you see up in the Siberia, Greenland, parts of Asia, and then, of course, all throughout Canada and parts of America, got up to 3 kilometers thick. So they were several miles thick. This is big stuff. And we're going to talk about how they developed. Now, I mentioned at the beginning that we recognize 13 cycles of episodes. And most classes that talk about glaciers, you'll hear about 4 fluxes, and they're named after the furthest travel extent of the terminal moraines. There are really 2 major terminal moraines and then lots of smaller ones, but the initial 4, with the Nebraskan, Kansan, Illinoisan, and then the youngest being the Wisconsin, we now recognize that they're 13 and we call them different names. So let me tell you how they have been delineated. Events number 1 through number 11, which would also have included Nebraskan and Kansan, I might add, are now called pre-Illinoisan ice ages A through K. I'm not making that up, A through K. We refer to event number 12 as the Illinoisan stage. And then the Wisconsin stage represents the last flux, the most recent of the ice advances into North America, and it primarily affected the Northeast. Having said that, we're going to learn a little bit about the ice packs and explain their importance because there wasn't just one. So let's get busy talking about the 3 types of glaciers, then we'll point out what the names of those glaciers are that were important during the last ice age. All of you know about valley glaciers. We learned about that in physical, and they are confined to mountainous areas where you get a tongue of ice that develops as snow falls, recrystallizes into firn, and then starts flowing under its own weight from high to low elevation. Valley glaciers were extremely prominent during the Pleistocene, and sometimes I've heard lectures where people forget to talk about the importance of valley glaciers, yet they'll talk about these remarkable landscapes like U-shaped valleys and horns and make it sound like continental glaciers did all the work. That is totally not the case. We had valley glaciers in Hawaii at this time on the top of Mauna Kea. So what I showed you in the last lecture with what I showed you at the beginning with the Grand Teton Fault, okay, so that's quite evident right there that that was glaciation. All of those features that you saw that made up the Grand Teton Range, those are caused by Pleistocene glaciers. That's evidence right there. So how is a valley glacier different from continental glaciers and then ice caps? So let's do continental glaciers next. There is really a definition for this. They must be at least 50,000 square kilometers in size, minimum. How are they different from valley glaciers? Not just in size. They have no confined topography, but more importantly, they flow outward from a single location core of their ice to an accumulation point. So they grow from a central location outward. Valley glaciers grow from a top down. So they're completely different on how the morphology works. Now they create some of the same stuff. They make different landscapes, but they certainly create deposition and cause erosion. Now, an ice cap is different from a continental glacier in this fact that it's smaller than the 50,000 square kilometers, but they're important because we're going to see some of each type during the last ice age. So what were the names of the 2 major ice sheets in North America? Mind you, we're only going to talk about North America here. The big ice sheet, which is subdivided into multiple pieces, is called the Laurentide. And the Laurentide makes up this big section right here. Like I said, there are multiple pieces of it, but I don't think we need to learn about each piece because that's a whole course in itself to talk about the 13 different advances and all the evidence we have for it. There is a second major ice pack that is right here called the Cordilleran, and it's an ice sheet, and it meets the definition of a continental glacier. So understand the size difference is critically important to the end result of how long it's going to take to melt these things. This one took about 12,000 years to melt, while this one took about 4,000 years to melt. Not a surprise in this shape, right? And the tongues of this one, where the furthest reaches of the ice came down, makes a very important landscape that we'll talk about in a minute called the scablands. Here we're going to see lots more braided streams and consistent melting that's going to create blankets of sediment, and I might point out where that sediment's going to go is right in the Midwest, making for some excellent fertile ground. So you need to make sure you know which ice sheet is which. The Laurentide's the big one, and most of the ice age is referred to, it's talking about the Laurentide, but you can't forget how important the Cordilleran was. Geologists, this is a super time to take a break before we start in on the glacial evidence of the last ice age. There's a lot of it, so get ready. It's more than what you learned about in physical, so stay tuned and see you back soon. Bye.